to understand carefully or better in detail. So wait, let me start again. We need to be able to understand what curly arrows really mean and represent in every mechanism, because in this way we can draw mechanism with logic rather than through memory. So the mechanism we're looking at now is the nucleophilic substitution. And this involves an halogen, doesn't really matter which one. So I'm just going to do a skeletal formula and an X. This X could be fluorine, chlorine, bromine, and iodine. And then Nu, it's any nucleophile. Nucleophile could be OH minus, could be NH3, BCN minus, any nucleophile which from previous lessons we know that are electron pair donors, so anything that is electron rich. Okay, so in this case, we won't focus too much on that. But let's take a nucleophile that has a negative charge. If it has a negative charge, it's because it has extra electrons than it had before. Okay. And for the sake of this explanation, actually, what I'm going to do, which is normally not what we want to do, because we want to do skeletal formula for this mechanism because it's just so much faster. But I will draw kind of dot and cross diagrams just to show where the electrons are. So let's say that this carbon has these the black crosses, okay, and then the other elements, they have the red dots, okay, which are probably hydrogens, which we don't really care, so we won't draw, but the halogenity is important. So to understand the movement of electrons, the curly arrows, first of all, we need to remember, like in any mechanism, this is like a clue to always have when we have to do any mechanism, is that, well, we know nucleophile, electron pair donors, they donate electron to an electrophile, which are electron pair acceptors. So that's what we always look for in a mechanism, nucleophile, electrophile, and then we can connect. However, we need to think about the next step. So if the nucleophile attacks an electrophile, then what comes after? Okay, and this is normally what differs in like the second step of the mechanism, or just this second curly arrow. So normally halogens are more electronegative than carbon, so there would be a negative dipole on them, which means that carbon will act as our electrophile, because positive dipole, it can be an electron pair acceptor or simply just electron deficient. So the nucleophile will be attracted to it. Let's see what would happen if, well, and that's what we know from the basic logic, or the basic that we've learned, right? So always nucleophile attacks the electrophile. Okay. Now, let's think about what is the consequence of that curly arrow in terms of electron. And is this enough? Can we stop there, or can we already work out the next curly arrow? So if this is the only curly arrow, it really means that this curly arrow, picture it as it's a new bond. Yeah, so those electrons, so this curly arrow connected the nucleophile and the carbon. However, this does not occur because notice how many electrons the carbon would have, which means that, and that's what we need to keep in mind. Oh, look, this is a new bond. Carbon has kind of not gained, but now it's sharing more electrons, because this is a dative covalent bond with the nucleophile. This means that one bond must break. And the most polar bond is the one that will break. And we know the polar is the one with the halogen, or anyway, the reactive one, because the others are other carbon-carbon bonds or hydrogens. So we know that that's not a bond that we keep in mind during the mechanisms. This means that at the same time, this bond must break. And it's really important to picture the movement of electrons. So I'm just going to try to animate it a little bit. So if this occurs, which should occur at the same time, all of this basically leaves the molecule. Yeah. So I hope you can picture it like that. So the curly arrow causes yeah, the halogen to leave. But notice how now the halogen has that extra electron that came from the carbon, and that's why it would take a negative charge. Okay, of course, when we draw the mechanism, this is completely unnecessary, but just I think it's useful to visualize it at least once so that when we have to draw quickly a mechanism, we can do it, but not just by remembering where the curly arrows are, but actually understanding the movement of electrons and the movement of the charges as well. So if we do quickly this mechanism from with a skeletal formula, we have a nucleophile of any type with a negative charge because it has a lone pair, or well, it comes maybe from from like a metal or whatever. It doesn't really matter where this negative charge comes from. We know that the positive dipole is on the carbon, the negative dipole is on the halogen. So we know that if there is a new bond formed from the lone pair of the nucleophile to the carbon, this would mean that there is an extra bond. Yeah, but as we've seen, and then hopefully you can now picture it in your mind, this movement of electrons, then one bond must break at the same time. Otherwise, carbon would have too many electrons, and we know that does not occur. And that's why in this mechanism, it's actually a one-step mechanism where there is a bond formed and at the same time a bond broken. And the consequence of that is, well, actually there is a change in where the bond is, but it doesn't matter. Actually, I don't want to focus on the stereochemistry for now. But we have this nucleophilic substitution where now the halogen, which is our X, now has a negative charge. Okay, so it's really important to visualize the electrons to understand. So to always have a starting point, nucleophile to electrophile, and then think about, okay, is there a second bond that breaks or is there a charge involved? But I think to do that, we really need to have clear the movement of electrons, and not by drawing them out like I did to represent it, but visualize it through understanding what those curly arrows really mean. A useful example here which requires, unless we know the mechanism, which well, I'd rather you work it out always through logic and through visualizing the movement of electron, is this one. Okay, because there are some charges that we have to work out. So first of all, as usual, nucleophile, electrophile. Well, the ammonia has a lone pair of electrons, so it's likely to act as a nucleophile. And then we know that the carbon, it's slightly positive, chlorine is slightly negative, which means that the reaction that could take place is between the nitrogen and the carbon. So arrows always nucleophile to electrophile. Carbon can't have more than 4 bonds, which means that the carbon-chlorine bonds at the same time break. However, something here has changed because nitrogen now has done a dative covalent bond. So nitrogen has 1 electron here, then it has 3 hydrogens. However, notice that electron is shared with the carbon, which means that nitrogen, because it has an extra bond, has kind of given away its electrons to the carbon in this dative covalent bond. And it doesn't have extras. It doesn't have a negative charge to start with. So nitrogen with 4 bonds, after having formed a dative covalent bond, will get a positive charge. Okay. And it gets a positive charge because it kind of has given away the electrons to the carbon. The chlorine, it would be negative. So guess what happens here? To maintain the neutrality of the reaction, because we don't have a charged nucleophile, we have everything is neutral in the first step, it would be, and also, well, to reform the neutral compound, the chlorine attacks the hydrogen or takes away the hydrogen, so that the electrons between those electrons, so between the hydrogen and the nitrogen, they go back to reform this lone pair, because as we know, organic products, they won't be charged. Yeah, and this would be the substitution overall with HCl as a side product. But I hope you, or just practice just visualizing the movement of these electrons and trying to fully understand. It's something that has to click by continuing trying to visualize the movement of electrons, not just as curly arrow, but really imagining the electrons as they moved from the nitrogen to the carbon. If it helps, try to redraw these and display the formula to really see where the electrons are and why there are charges involved. And then this is just a little bit more complex because we need this extra step, but remember that nucleophilic substitutions, they will all be the same. So nucleophile to electrophile, and then carbon-halogen bond will break. But we could have that extra step if we start with a neutral nucleophile. So take a list of nucleophile and some haloalkanes and try to practice drawing the mechanism, and you will notice that the arrows are actually always the same. And if there are charges involved, well, that's try to visualize it by looking at the movement of electrons.